Let's talk about leprosy. An illness rampant centuries ago has decreased in prevalency but hasn't vanished. 200,000 cases are reported each year, dominant in Asia, Africa, and South America. Its minimal prevalency is fascinating and worthy of exploration. Leprosy leads to skin lesions, peripheral nerve damage, and the degradation of motor and sensory functions. Leprosy arises from the Mycobacterium leprae, or M. leprae. It enters the body through the nose, not the skin as once believed. Furthermore, transmission is supported by the respiratory system. M. leprae depends on specific attaching proteins called adhesins. They are on the bacterium and stick to the epithelial skin cells in the respiratory tract. Our body's response to foreign pathogens happens through both innate and adaptive immunity. Once Lepromatous bacteria has infected the host, our first line of defense, or our innate response, is carried out by three main cell types: macrophages, dendritic cells, and keratinocytes. Macrophage cells recognize surface antigens on infected cells by binding with receptors on the macrophage. There are two types of macrophages. M1 macrophages carry out inflammatory responses causing skin lesions. M2 types are activated for further adaptive responses and carry out phagocytosis, a method of engulfing infected cells. Dendritic cells ensure good transmission between neurons to maintain motor and sensory functions, along with skin healing. In passive immunity, these cells are important messengers that aid T-cell receptors in identifying infected cells. Dendritic cells affected by leprosy could cause nerve damage. Keratinocytes are skin cells that are helpful in the innate immune response through increasing cytokine activity for cell-to-cell signaling and recruiting cells to amplify the inflammatory response. Adaptive immunity helps deal with progressive lepromatous cells and helps with targeting them. T cells play a role in this, and their responses come in two forms: Th1-mediated responses through the use of polar or charged M1 macrophages and cell signaling pathways restrict leprosy spreading. In Th2 responses, T cells are less present and instead deploy different substances like cytokines and interferons, thus inhibiting macrophage activity and progressing the disease. Differences in these responses trigger inflammatory outcomes. Both expressions result in skin lesions via leprosy. Here ends our talk of the longevity and legacy of leprosy. Will leprosy soon leave us forever, or will it remain, haunting us like the ghost of immunology past?